This is the first lecture of Advanced Geomechanics PGE3A3. We're going to start this lecture by revisiting basic concepts about stresses in the subsurface. And in order to motivate this first lecture, I'm introducing this plot where we have a record or a log of stress as a function of depth. Depth is in the y-axis, and here we have pore pressure, minimum horizontal stress, vertical stress, and maximum horizontal stress. And you can see that those stresses vary as a function of depth, and so does pore pressure. Something important to notice in this figure is that sometimes horizontal stresses can be larger than the vertical stress. Okay, so let's see why we have three stresses and why stress is different uh, to pore pressure or, for example, to fluid velocity. All right, so today, let me add the date over here. It's 2020, August 26, and the first thing that we're going to do is to talk about introductory concepts. And in order to do that, let's imagine the ground. And in the ground, we have here a wellbore which has been drilled out of a drilling rig and goes into a particular formation. Okay, first of all, let's see typical properties that we look at in a given reservoir. And probably the main one that we care about, in at least in reservoir engineering, is reservoir pressure. So let's say that at a point somewhere over here, we have a pressure at the point P, and we call that pressure P. And that pressure is just going to be one value. In this same point, for example, we could also have a temperature. A temperature is just going to be one value. These quantities that are just one value, regardless of what the coordinate system is, are called scalar quantities. And this is where we're going to marry geomechanics and linear algebra in order to get started. So examples of scalar quantities are, as I was saying, uh, let's not use equal, are going to be pressure, denoted by P, and also temperature. For example, pressure could be 10 megapascals. Temperature could be 100 degrees C. It doesn't matter what is your coordinate system. Here, let's draw it as 1, 2, 3. This value is going to be the same. This is not going to happen. What I just say is not going to hold when we look at another type of quantity, which is called a vector. Can you think about an example of a vector in reservoir engineering and geomechanics applications? Okay, let me tell you one. It could be, for example, when the fluid moves from here to the wellbore, and let me add, I'm going to add a fracture here in a little bit, but when a fluid moves, because I depressurize a fracture, this is going to move in a given direction and with a given magnitude. Therefore, in this case, I'm going to have a velocity. denoted by V, and also by this line that indicates that it is a vector. The velocity, if we're working in a three-dimensional system, is going to have not just one value but three. It's going to have three components. Like, for example, it could be moving according to the coordinate system that we just have here, 1, 2, 3. Let's say that it just moves in direction 2. So the first component is going to be 0. The second component is going to be, let's say, you see this going in direction opposite to 2. So let's put 0.1 meter per day. And let's say it's not moving in direction 3 either. So this component is going to be 0, 2. And now we have a vector. We have a vector with quantities that depend on the coordinate system that you are referring to. If I change the coordinate system, I'm going to change what these values are. So the numerical values that go into a vector, they depend on the coordinate system. And for a three-dimensional space, we are going to need three values. Let me fix this. So I make this vector consistently regarding dimensions. Okay, and I was saying that here I will add a fracture, and let's say that in this wellbore we did a fracture which is vertical. When that fracture happened, another example of a vector could be the displacement of the rock as it moves to the center to the surface of the rock. That displacement is, we're going to call it U. And with the coordinate system that we have here on the top, that displacement also is going to be in direction number 2, 0 in direction number 1. Let's say in direction number 2, it's in the direction of 2, so it's going to be positive. Let's say 1, 0 centimeters. Those are examples of vectors. And the third example that we're going to see is the one that we are most interested in this class, and probably something which is new to some of you, which is a tensor, and that's going to be stress. In this case, actually or rigorously, this is called a second order tensor, and a three-dimensional space is going to have 9 components. So you see, for the scalar, we just had just one value or one component. For the vector, we have 3. For the tensor, we're going to have 9. An example of such tensor is going to be stress. And stress, we're going to refer to, especially to effective stress, as sigma. And sometimes this tensor goes with 2 lines. That means it's a second order tensor. And as I was telling you before, it's going to have 9 components, and we're going to express it with a matrix. This matrix is going to have components sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, and sigma 3, 3. And this is going to apply to any point in this continuum. So, for example, it's exactly the same, but just let me draw this over here. I'm going to be referring to the state of stress. in this cube in this section of the reservoir. And we would like to calculate those stresses, and that's going to be the first objective that we're going to have in this class. Similar to what we were saying before, for the case of the vectors, notice that the stress is also going to depend on the coordinate system. If we were to have another coordinate system in another direction, for example, a coordinate system which is rotated and now is uh, like this. Let me try to draw it again. And here, of course, we are always following the right hand convention. So let me just do it radically different, this one. Okay, this is the coordinate system 1 prime, 2 prime, 3 prime. If I were to write or to put numerical values in a vector or in a tensor like stress, the values that go inside here will be different if I have a different coordinate system. All right, so let's see a few things, a few characteristics about the stress tensor that are quite important. And in order to help to that, we're going to make another schematic of stress. So as you saw for velocity or for displacement, the physical interpretation, it's pretty evident from these arrows over here of a velocity or of a displacement. For stress, it's a little bit more difficult, and so we're going to require to make another drawing over here. And we're going to use the coordinate system that we were using before with 1, 2, 3. These vectors 1, 2, 3 are called the element, the components of the coordinate system. And here I'm going to draw the cube that we had there on the top. So this is going to be one face, and these are going to be the 3 other faces. And here, the physical interpretation of stress is going to be the stresses that are applied on this cube. So let me use different colors over here. When we refer to stresses which are normal to the face of the cube, we are going to refer as those to normal stresses, okay? And these normal stresses are going to be, for example, sigma 1, 1, sigma 2, 2, and sigma 3, 3. Here in this notation, the first index denotes the phase of the stress. The second index denotes the direction. When those two coincide, as in the ones I have just written here, that's a normal stress. For example, sigma 2, 2 is the stress applied on phase number 2 in direction number 2. Let me tell you what I call phase number 2. Phase number 2 is the phase which is perpendicular to direction number 2. So in this particular case, this is phase number 2 because it is perpendicular to the direction 2. And since the stress is in direction 2, this is a normal stress. These normal stresses are going to be located in the matrix of the stress tensor in the diagonal of the matrix. The other type of components that we're going to have are shear stresses. And let's start with the shear stresses on phase number 2. Since we already have phase number 2 over here, let's go with phase number 2. In phase number 2, we are going to have the stress sigma 2, 3, because it's applied on phase number 2 and it goes in direction 3, and sigma 2, 1. Something that you should notice over here is that I'm drawing all of these stresses in what is by convention assumed to be the positive direction. And this positive direction by convention in geomechanics is going to be compression for the normal stresses, and the same is going to apply to the shear stress. And the convention is that the positive direction is going to go in opposite direction to the direction of the elements of the base 1, 2, 3 when you are on what is called a positive phase. In this case, this phase number 2 is not only phase number 2, but it's also the positive phase of number 2. Wait a minute, this went full screen. I didn't want that. Don't know how to get out from here now. Okay, so just one sec. Okay, all right, so this is the positive phase number 2, because in order to get to this phase, I need to walk a positive increment in direction number 2. Well, fantastic. My Microsoft Note just crashed, but fortunately it opened up right away. Okay. A positive difference or a positive walk in direction number 2 is going to lead me to the positive phase. In this positive phase, as I was saying before, the arrows of stresses, if they are positive, they are going to be pointing in direction opposite to the elements of the base. All right, so if we continue, then let me get out of full screen again. Okay. If we continue with the shear stresses, here we're going to have sigma 3 in direction 2, and this is going to be the shear stress sigma 3, 1, and on phase number 1, this is going to be sigma 1, 3, and this one is going to be sigma 1, 2. The shear stresses in the stress tensor in the matrix are going to be located in the off-diagonal places. And a property of this matrix and a property of the tensor is that this matrix is symmetric, and therefore sigma ij is equal to sigma ji, or sigma 1, 2 is equal to sigma 2, 1, sigma 1, 3 is equal to sigma 3, 1, and so on. This is the reason for this is that this stress element is under equilibrium, not only equilibrium of linear momentum, but also on the equilibrium of angular momentum. And a condition of that is that, as you can see, for example, here the stress sigma 3.2 and sigma 2.3, they have to be the same such that this element is in equilibrium. If these stresses are not the same, then this element will start to rotate and it will not be in equilibrium. So because of that condition, these are the same, and this is what is called a symmetric matrix. All right, when we have a symmetric matrix, because we're also dealing with real quantities, that's going to mean that the values of the stress tensor are real numbers. If we have these two conditions, this is going to lead to a property of a matrix which are called eigenvalues, which are also going to be real numbers, and they are always going to exist. I don't know if you remember from linear algebra what these eigenvalues are, but these eigenvalues are characteristic values of a matrix, and these are going to be three numbers. So for any matrix, symmetric matrix, we're going to have real eigenvalues and real eigen vectors, and in mechanics what that is called is the principal values and the principal directions. And we take it one step further into mechanics, and if we apply this to the stress tensor, this leads to the so-called principal stresses of a matrix. And those principal stresses, let me call this sigma p for principal stresses, are going to be a set of value such that we can write our stress tensor just with three values, sigma 1, sigma 2, and sigma 3, and in the diagonal, and all the off-diagonal values equal to 0. You should keep in mind that this is the same stress tensor as the one we had before, with non-zero values in the diagonal. But the only thing that we are doing is just looking at the direction such that the stress tensor now can be written just with these three principal values. Let's come back to the example of the vector. You remember in this case that for a velocity, we could write this vector such that the other components are 0 and just one component is non-zero. Well, if we were to choose, for example, for the same vector to write this vector in this other coordinate system with the primes, then now all the components will be non-zero. Well, it's the same thing with the stress. If you find a particular coordinate system that aligns with the principal directions of stress, you can always write this stress tensor with the principal stresses. And related to these principal stresses, also we're going to have the principal directions. For example, in field conditions, many times vertical stress is a principal direction, which makes the other two principal directions to be horizontal. A property of these systems is that the principal directions are always going to be perpendicular to each other. All right. Let me come back to the problem that we started with. Now we have principal stresses. Those are in general different values from each other. Let me add this in here. Sigma 1 in general is going to be different to sigma 2, and it's going to be different in sigma 3, and these are going to be the principal directions. Usually we write this matrix such that sigma 1 is the first element and is the largest, most compressive. We put it at the top. In the middle, we put the intermediate stress, and in the bottom right, we put the least principal stress, sigma 3. All right, so let's come back to the example that we started with. And here you can see that we have a plot of stresses as a function of depth. Now we see why we have three stresses: vertical stress and horizontal stress. In this case, also we assume that vertical stress is a principal stress. Therefore, the other two principal stresses are going to be horizontal. And the least principal stress in this case is going to be the minimum horizontal stress, here denoted by a small lowercase h, and the maximum horizontal stress denoted by capital H. And in this example, we see those stresses, how they vary with depth, and how sometimes they can get larger than each other. We're going to see the implications of these changes in the following lecture. But so far, summarizing, we have seen what is the stress tensor, why it is different to a scalar and to a vector, what are normal stresses and shear stresses. Let me write that down over here. Shear stresses here are in brown, and normal stresses in blue. For any stress tensor, we can compute what are called the principal stresses, in mathematical terms called the eigenvalues, and that's going to characterize that stress, and it's going also to tell us what are the principal directions. Practical application of a principal direction, for example, of the least principal stress, is that hydraulic fractures are going to tend to be perpendicular to the direction of the least principal stress. All right, just to close this example, I'm just going to do one more thing, and I'm going to add some numerical values to the stress tensor that we have started working with here. And at this location, let's say that this is at about 10,000 feet. A ballpark estimation of what the total vertical stress is going to be. Let me write this stress tensor over here. We're going to see later on why we call this S. But if I write the stress tensor in the coordinate system 1, 2, 3, then the component in direction 3 is going to be S33, and that's going to be the vertical stress. Usually, a rough estimate of vertical stress on shore is 1 psi per foot. So here we're going to have 10,000 psi. I'm going to assume that this is a vertical, this vertical stress is a principal stress. Therefore, this is going to be 0 and 0. And for the horizontal stresses, I'm going to assume also that in direction 1, we have the maximum horizontal stress, and in direction 2, I have the minimum horizontal stress. A rough estimate of what is the minimum horizontal stress for a place which is in a tectonically passive environment is about 60 to 70% of the vertical stress. So for direction number 2, then I'm going to write here that this is 6,000, let's say 500 psi, and the intermediate stress is going to be somewhere in between the minimum value and the maximum value. So let's say here 7,000 psi, and this is in the coordinate system 1, 2, 3. It looks pretty much like the matrix of principal stresses, but here notice that these are not ordered in according to the principal stress direction. This is written in the coordinate system 1, 2, 3, so I'm following these directions. All right, this is it for this video.